In this video, we're going to talk about the indefinite integral or the antiderivative. Those terms mean the same thing. The word antiderivative is more suggestive of what's going on. So what is the antiderivative? Well, let's imagine we have a table of integrals, and someone comes along and says the derivative of a certain function is the cosine of x. What's the function? Well, that function is called the antiderivative of the cosine of x, and we can go to our table and look up the antiderivative or the indefinite integral. That's the thing that differentiates into the cosine. Notice that k there. That is a constant, some unknown or as yet undetermined constant. And we can stick that on our function because we know the derivative of a constant is 0. So the antiderivative is not completely determined. If we know the derivative, we don't know exactly what the antiderivative is. There's a constant that we still have to determine, and you determine that by initial conditions. And we'll look at some examples that will make that clear. But this is also why it's called the indefinite integral. Back here, we don't know exactly what it is. It's indefinite. So how do we calculate the antiderivative in general? Well, let's look at a little table here. Let's look at our simplest differentiation. If we have a polynomial, x to the n, we know how to differentiate that. First, we take that exponent and we multiply by the exponent. So it's n times x to the n, and then we lower the exponent to n minus 1. So suppose we wanted to undo this differentiation. And I'm going to forget about the constant for a second. We always know that we can stick a constant on when we're all done. But let's leave that aside for a second. So suppose we're starting here and we want to go backwards. Well, we have to reduce the exponent. That brings it down to n. Or no, well, actually, if we're going backwards, we want to do the exact opposite. We want to increase the exponent. So it goes from n minus 1 to n. And then we want to go backwards again. So instead of multiplying, we want to divide by n, and we get our starting point. Now let's apply that sequence to something that doesn't look exactly like where we ended up before. We still apply the same sequence, though. If we're given an x to the n and want to find its antiderivative, the first thing we do is increase its exponent. So we have an exponent of n plus 1, and then we have to undo multiplication, so that's division, by the new exponent. Notice it's the n plus 1 that we're dividing by to get this. So remember that when you're differentiating, you end up multiplying by the original n, this n up here. But when you're integrating, you don't end up dividing by the original n, you divide by the incremented n, the n plus 1. Okay, so we're going to use that in a number of places when we look at some examples, but let's look at another situation. Suppose we have a composition of functions, a chain rule situation. We know how to differentiate that. We first differentiate the outer function, that's f in this case, that's f prime, and we evaluate it at the inner function. Then we multiply by the derivative of the inner function. So that gives us this g prime of x stuck on the end there. So now suppose we are given this thing here to start with, and we want to know what the antiderivative is. Well, it's a two-step process. We first divide by g prime of x to get back to this level. Then we say, okay, let's look at that outer function. It's f prime. I have to take the antiderivative of the outer function and evaluate it at the inner function. So I end up with f of g of x. So let's apply that process to an example here. Suppose I see this and I want to know what the antiderivative or the indefinite integral is. So first I identify the outer and the inner function. The inner function is the squaring function, and the outer function is the sine function. And this just fits the pattern. If I differentiate my inner function, that's x squared, I get 2x. So that's the g prime of x. So this, you have to fit this pattern exactly to use this reversal of the chain rule. It can't be have some of the pieces and not others. It's got to have exactly what g prime of x is in there. So in this case it does. So the first thing you do is you divide by g prime of x to get the just f prime of the inner function. Then you say, what's the antiderivative of the sine? It's the cosine, because that's one of our functions in our table of integrals, and it's one that we've studied. And we need the minus here because when I differentiate the cosine, it throws out a minus, and there's no minus over here, so I have to put a minus out front to kill the minus that the cosine, the differentiation of the cosine causes. So we end up with this as our antiderivative. So let me emphasize one more time. When we suspect we're in a chain rule situation, we have to identify that inner function and see its derivative precisely. No fudging there. You've got to see g prime of x. All right, let's look at some examples. Let's go over here. We'll start simple. This is the notation you use. This symbol there means the integral, or the antiderivative of x cubed, or the thing that if I differentiate, I get x cubed. And this is a simple one. This is our polynomial situation. So let's just follow our rule for that one. And again, stop the video and try these yourself, and then check with the video. So the rule says, first what do? We increase the exponent and then divide by the incremented exponent. So this is going to be x to the fourth, and then we divide by 4. Notice we divide by the thing we end up with, not the 3 that we started with, but with the 4 that we end up with. That's because of the order of things that we had for differentiation. The multiplication comes first and then the reduction. So when you do the opposite, you got to increase and then divide by the new thing. So that's our answer for that one. Now let's look at this one here. This one you can always take constants and move them outside the integral, because integration again is a linear operation. I haven't proven it, but since differentiation is a linear operation, integration is also a linear operation. Notice this number here, the 0.32 that we started with, we still have it even though we've moved the 5 outside. And now this thing inside is just what we had before. So this is going to be 5 times x to the fourth over 4. And we have our 1 there indicating we are good. And let's look at this one here. This is again a simple one. K is a constant. If you don't see an x in it, then unless something else is said about the term, it's assumed to be a constant. So again, we can move that k outside and get rid of it inside, and you've got the same numerical value there. And then we remember what the derivative of the sine, the cosine, they turn one into the other. So we know this is going to be k times the cosine of x, or maybe the negative cosine of x. I always have to think for a minute. Well, this is the program is telling us it's probably the negative. Let's see if that's true. Well, let's just, if I differentiate the cosine, what do I get? I get minus the sine. So I need to put a minus in front of there. Oh, I still didn't get it. Now why is that? Well, the reason is this is the indefinite integral, and the the program in computing this may have chosen a different constant. So I think if I put plus k here, then we get equality. I have to choose the same constant that the program chooses, and usually it's this function here evaluated at 0. That's how the program chooses the constant. It could be anything. So it says let's let x equal 0, and that's going to be my constant. And we know the cosine of 0 is 1, so that constant works out to be minus k, and when we add it back on, we get the equality that we want. Don't worry too much about that. Just remember that I don't. This thing over here on the left is not precisely determined. There's always a constant that's floating around someplace, and we'll see how to determine that constant in physical problems. It's the initial conditions that determine that constant. So for now, though, just concentrate on the fact that if I want the antiderivative of the sine, I know it's the cosine, and maybe it's minus the cosine, maybe it's plus the cosine. You have to think for a minute about that. All right, let's go on to the next one. Okay, now I got sine of 5x. So this is really a chain rule situation, but this is so simple. Generally, you don't think in terms of chain rule. You just say, okay, I know it's got to be cosine of 5 times x somehow. But then you look at it for a second and say, well, if I differentiate this right-hand side, this cosine of 5 times x, the inner function is 5x, so it's going to throw out a 5. But I don't see any 5 over here. There's no 5 on this side, so I got to do something to kill that 5. So I multiply by 1 over 5, and now when I throw the 5 out, it's going to kill this one. And you got to think, is it sine or is it plus or minus again? And what's the derivative of the cosine? Well, that's a minus, so I have to put a minus here also. And I still don't have equality because, again, this is choosing a certain value for k, and I think it's going to be plus 1/5 is what the program is choosing. Let's see. Yes, so that's what, again, it lets x equal 0 and evaluates that. And so you have to add it back to get the equality that we want. All right, let's go on to another one. Now, here's a tricky one. What is this one here? Well, it's definitely, it looks like a chain rule situation. My inner function is x squared. So if I want to integrate that, I have to see the derivative. It has to be times the derivative. So we're looking down here. This is what we're looking for. We're looking for some f prime times g prime of x, or sort of like this here. Well, we look at this for a second. We say, oh, I don't see the derivative of the inner function. The inner function is x squared. So here's what I'm going to do. I know the derivative of x squared is 2 times x. So let me just throw that in there. 2 times x. And then I'm going to divide by 1 over 2 times x out here. And I haven't changed anything. Well, you have. You can never push x's outside the integral sign. You can only push constants outside the integral sign. You could put a 2 in here and divide by 2 and push the 1/2 out, but you cannot push the x out. This dx here tells you which is your variable of integration, and you can't push that through the integral sign. It's not like a constant. You just can't do it. So you can't do this, so we got to go back and look at this again. So we can't use our chain rule here. Let's see what the program says about this. Now, remember, the way the program works, or the way you work before there are computers, is you'd go to a table of integrals and you look through this side here and try to find something similar to the sine of x squared, and then then you look on the other side of the table and find the integral. Now this program has a table implicitly in it, and it looks through about 100 of these. We've only shown 7, but there are many more pairs in a table. Let me just see what the program is going to say about this. See if it can find any antiderivative of sine of x squared. So if I do this and it returns nothing, it leaves it the same. So that shows me that of those 100 items in the table, this doesn't match any of them. This thing doesn't have an antiderivative. There's something called the definite integral and something called numerical integration. We can come up with a function that gives us an antiderivative, at least formally, but there's no known function that differentiates into this. So we're going to have to talk about numerical integration and the definite integral somewhat later. But occasionally you do run into, not occasionally, quite frequently, you run into functions that you can't integrate. You can't find the antiderivative. Now let's go on and look at the next one. The next one, what would I need in here to make this differentiable, or to make it integrable? Well, I need a 2x in there, times 2x. Well, it's sufficient that I have just an x in there, because remember, I can always multiply by a 2 in there and then put the 1/2 out here to compensate for it. And if you look at my numbers here, that putting that 1/2 out there doesn't change the value of this integral. This is the one I'm looking at right now. This and this are the same. Okay, now I can use my chain rule to find the antiderivative or the indefinite integral. So let's try that. The chain rule says I first divide through by the derivative, and that's 2x. Well, first of all, I have to carry that 1/2 along, times. Then I divide through by the 2x, so that disappears. And then I take the antiderivative of the sine. And I know that's going to be the cosine, and I evaluate it at the inner function. And you got to be careful here, because this one, is it a minus or a plus that I have here? So you got to just remember that the derivative of the cosine is minus the sine. So that means I should probably have a minus here. And then to get the equality I want, I have to figure out what the constant is. And the cosine of 0 is 1. So I think this is going to be 1/2, I hope. Let's see what happens. Yeah, that's the constant that the program is using. So I have to know what it's using in order to get the equality that I like to see. Let's look at another of these. Okay, here's exp. I put some functions down here and their derivatives. We haven't studied these yet. We haven't proven that the derivatives are what I'm saying they are here. We will get to that a couple of videos down the road. We can still use them as for illustrative purposes, since our process is strictly a formal one. All right, so look at this here. What you see, that g of x there, what comes to your mind? Well, what comes to your mind is the chain rule. I've got f of g of x, f of g of x. So I want to use the chain rule. But remember, to use the chain rule, you've got to see that g prime of x, and I don't see it. So this is one of those functions that's doesn't have an antiderivative. Unless g of x is something very simple. If g of x was like 3 times x, then we could go through the process we went through a short while ago with sine of 5x. But if it's an x squared in there, then we're in trouble. So what do we need? What would we like to see? What function in there could we find the antiderivative of? Well, we have to see a function where we have to see g prime of x in there. And we can't just add it in. So you can't, I'm not showing you how to differentiate that original function. I'm showing you a different function that we can differentiate. And just out of curiosity, let me see if the program is smart enough to integrate this thing. I don't know if it is or not. If it is, it means this form is on our table, one of our 100 items on the table. Okay, yes, it got it, e to the gx. So that is an integral on my table of integrals. All right, let's go on and look at a couple of more here. Let's look at this one here. All right, well, I have e to the x cubed 5x. And I'm thinking, oh, this is a chain rule situation. So my inner function is x cubed, and the derivative of x cubed is 3x squared. Whoops, I have a 5x. I don't have an x squared, so I'm in trouble. I can't find the antiderivative of this. But now, let's look at another function. Again, I'm not showing you how to differentiate this function or integrate the function I have up there. You can't find an antiderivative. Let's look at a different. Now I see the x squared, and it's x cubed. The derivative is 3x squared. Well, I don't have that, so aren't I in trouble like before? Well, no. Remember, constants you can always move outside. So I can put the 5 out here and divide by 1/3 and put a 3 in there. You know, that's how you think about it. You really just do it all in your head. And now this is precisely the situation that I want. So to find the antiderivative, I carry along the 5/3. I divide by my derivative, by g prime of x, and I take the antiderivative of e. But let's go down to our table. What's the antiderivative of the exponential function? It's the exponential function. So this is going to be times exp of x cubed. You evaluate that outer function, or the antiderivative of the outer function at the inner function. Notice you don't integrate the inner function and put like x to the 4th over 4 there. X to the cube stays the same. And we still don't have equality because of a constant different. I think this is going to be just 5/3. Let's see. No, maybe it's plus 5/3. It's neither of those. Interesting. I'm going to stop the video for a second. I have to think about this. Yeah, it is minus 5/3. I made a mistake back here, or I left something out of my formula. I left this times out of there. If you go back a little bit in the video, you'll see there's no times there. So this side of the formula didn't even make sense. But again, to get this constant that the program is using, you evaluate this function here, just a pure pre-constant function at 0, and then subtract it off, and then the program will agree with your answer. All right, what do we want to talk about next? Let's see, I forget, but we go to figure 3. Okay, yeah, this constant. How do we determine this constant? Well, the situation we're dealing with is called a differential equation with initial condition. Suppose, for instance, we're told that the derivative, dy dx, is the cosine of 3x. And then we're given an initial condition. It's where this process that the differential equation is describing starts. So we say when x equals 0, y equals 5. So how do we solve that? What is the y that satisfies both the differential equation and the initial condition? Well, the first thing you do is just look at the differential equation. We know how to find the antiderivative of the cosine. That's the sine. So this is where we are right here. We know that if we differentiate the sine, we get the cosine, and we're going to throw out a 3, and I don't see a 3 up here, I just see cosine. So I know I have to compensate by putting a 1/3 in front. Then I have my constant of integration k, which I don't know yet. But we know that here's our initial condition. Someone for some reason is telling us when x equals 0, we want this function to have the value 5. So let's plug x equals 0 into the indefinite formula that we have so far. And notice we have the only unknown now is k. We know what y of 0 has to be because someone has told us that they want that to be 5. And the sine of 0 happens to be 0. But you don't even have to evaluate that. You can just solve this thing for k right now. Even if you didn't know that the sine of 0 was 0, you could at least formally solve for it. And you get this formula. But of course, this is going to be 0. So let me just stick that in there. We know the sine of 0 is 0. And that's our full solution now. K has been determined. Let me temporarily put it up here in my value. And then we can go back and check things. Go back and look at this. And why isn't that working? Well, I have a test function up here, but I don't have the one that I'm currently looking at. And let me, so now this is true. And if I differentiate this thing, will I get cosine of 3x? Well, do it in your head before I do it with the program. The k is going to get killed, and everything else is going to work out nicely. So if I differentiate, I get the cosine of 3x. And just for numerical purpose, let me transfer it up here to my test function. Okay, so we've got the right derivative, and now let's take our function here and apply our initial condition. Again, we see the 1, so it's saying it's true. We've evaluated the function at 0, and it came out to be 5, so our k is correct. Let's look at one more of those. Same idea, but the derivative is a little more complicated. So you start with this here, and that's y prime of x. And why isn't it giving me a 1 here? Because I haven't changed my test functions yet. I will as I develop the problem here. But first thing we want to do is just integrate that, and it's going to be an indefinite integral. There's going to be a constant in it that is as yet undetermined. So you do that in your head. I'm too lazy. I'm just going to let the program do that. And if I ask the program to do that, it says that this is the antiderivative plus some constant, and we're calling our constant in this case k. So I get this formula here. Okay, I get this formula here for y of x with the k in it, and that's what I have up here. And if I want to know what k is, I go back and look at my initial condition. Here we're being told when x equals 1, we want y to be 0. So we have to substitute x equals 1 into our preliminary equation. And we get this. And we're told that y1 should be 0. So let me substitute that in there. And then we just solve for k like we did before. Just simple algebra. Again, I'll let the program do it because I'm kind of lazy. And that's our k. And let me put that in our numerical value just so we can do some checking here. So this k is actually 1/2. If you work this out, if you went to a table or calculator and figured out what the cosine of 4 is, you would see that k is 1/2, or approximately 1/2. All right, now how do we test that again? Well, let me go up and bring my function up again, because I want to differentiate it. I'm just doing a test now, and I'm going to put that in my test function. Then I go back to this thing here and see if that's true. And it is, and I've defined, if you look over here at dy, I've actually defined it to be y prime of x times dx. And dx is some small number. That way I can check my original formula against dy dx. So that looks good, and we know that the evaluation is going to come out right, because that's how we found the k. But this program, if you just drag and drop, it will do everything you need to do. And there we have something that's not true. So that's interesting. We've got to think about that for a second. All right, the reason it's not working, I haven't made this substitution yet. I still have as my test function, my old y of x. So let's put that in there. Okay, so there it is. That's a test. If you evaluate my function at 1 and you put that k in there, and again, what's k? I can substitute that in there if I want, I think. It collapses. That k collapses what's in there. Let me undo that again. It happens so fast. The k that we have in there is in fact the opposite of the rest of it. So once I make that substitution, the formula collapses to 0. So that is how you figure out what the constant is. You have to be given additional information, which will come about from some problem in physics, say. And now finally let's say one last thing about those functions that didn't have an antiderivative. First of all, here's a polynomial. We can find the antiderivative of that, but we saw we were having trouble with things like this, a sine of x squared. We couldn't find an antiderivative of that. And let's consider something even more complicated. Our formulas up to now have always just been functions of x, but we can also stick a y in there and say our derivative now depends on both y and x, and ask ourselves, what's the antiderivative that will differentiate into that? It's a valid question, and we'll see some examples where this will become a little clearer. But again, you probably can't do that. You can't go to a table and find this on the table and it'll tell you what the antiderivative is. But there's something called numerical integration that'll allow you to calculate the numerical integral of any form like this, of any function like that. In particular, we could be given the specification that the derivative of y of x has to be y of x, and ask what y of x is. Turns out that specification or requirement, along with the initial condition that y of 0 equals 1, completely defines the exponential function. So we go back to this table. If someone tells us we want a function whose derivative is itself and its value at 0 is 1, then that's a unique function. And the single property, or really the two properties, that its derivative is itself and its value at 0 is 1, that'll allow us to prove all the usual properties of exponentiation that we like to see. So we sort of go backwards. We don't start out with a function, an exponential function, and then prove what its derivative is. We go backwards. We say we want a function whose derivative is itself. Let's create one using numerical integration and then prove things about it. So that's what we're going to do in the next module.